How's it going, everyone? Today we're going to be talking about disk analysis. As always, most images were created with Crayon, some were taken from Wikipedia, and I always use the appropriate license. So we're going to start with a little bit of a review. We're going to briefly cover what metadata is, viewing files as hex with the hex editor, exploring inline metadata, and then we'll get to disk analysis. We'll talk about imaging, layers, the Sleuthkit, and Autopsy. So first, some review. Let's talk about metadata again. At its highest level, metadata is data about data. For a painting, that might be who painted the painting, when it was painted, its medium, and so on. For computers, metadata is facts about a file, such as its timestamps, its owner, its group, its permissions. And this data can be stored either in the file system or sometimes inline. And with the painting analogy, inline metadata might be the signature of the artist. So first, files as hexed. Last time we covered the default way to open a file involves a lot of interpretation. This text on the side here is the hex editor view of a file. But when you open a picture like this, it doesn't show this. It shows a picture, as you would expect. But we can use the hex editor to look at the bytes without any interpretation. And we saw magic bytes. The first two bytes here, FF and D8, those stand for JFIF images. So let's take a more in-depth look at that. Last time we talked about EXIF tool. But first I'll list the contents of this directory so we know what we're up against. Alright, so here's all the files. I'll use EXIF tool to look at some of the metadata of cat.jpg. Here we can see all kinds of information. And some of this is file system information, and some of this is actually inline metadata. We'll highlight some inline metadata with our hex editor. So this is in the same folder. So here's the hex view of that file. Just to demonstrate again, if I just double click on this file, an image pops up. But I'm actually looking at the individual bytes of this image right now in this hex editor. And I can see things like the file modification, date, time, isn't going to be in this file in the hex editor. The file size isn't going to be there either, the file name. All these things could be there, but typically they're stored on the inode of the file system for the file. But some things are inline in the data, like this. Here's this string. You can see that is actually in the data of the file. And so is this license string. See, that's here. So that's just to illustrate that some metadata is stored in a file and other metadata is stored in the file system. So now let's talk about disk analysis. This is one of the most core concepts of a forensics analyst. The first thing we're going to talk about is imaging. So we analyze these disks through software, through operating systems and other tools available there. And we work from a copy. Now there's this principle in forensic analysis that you always want to work from a copy. You never want to be working with the original data because you never know when you'll accidentally modify it. So we're going to use DD for this file copy. And DD can be used on the file or the disk partition or the entire disk itself. So let's look at this in the terminal. Let's just try running DD. So that doesn't really do anything. Well, it's doing something, but not what we are expecting. Let's try -H. Okay, it doesn't recognize that, but it tells us --help works. And it looks like we are just getting the tail end of this. So let's press the up arrow and then pipe to less. And here's some usage information. It says, copy a file, converting and formatting according to the operands. So it copies the file, it can convert and format according to different specifiers. Our most important options are going to be IF, which stands for input file, and OF, which stands for output file. And BS, which stands for bytes here, is how many bytes to read at a time, which the default is 512, but I think you can get a lot faster speeds by using something more like 32,000, 32 bytes, megabytes. So let's look at our directory again. Let's use DD. The input file is going to be hello. Output file is going to be hello3.txt. Says 13 bytes copied, and it took like 0.02 of a second to do that. So yeah, there's a new file. It's the same size as the original file, so that's probably a good indicator that it copied correctly. But we can check it really easily. So yeah, that matches. Now one thing you have to be really careful with DD is what you use for input and what you use for output. If you get it wrong or backwards, you can accidentally erase a file. And that's a bigger deal when we're dealing with disks. We don't want to erase our disk accidentally. So I'll demonstrate getting it backwards. So input file equals hello2, which is a blank file. Output file equals hello.txt, our original file. We'll do that. It says 0 bytes copied. That's probably a warning sign. If we look at that, now hello is 0. And it's empty. So that was bad. Thankfully, we have this backup copy, hello3, that we can just copy from and restore it. But just be really careful when you're inputting the input file and the output file. You want to get those right. You don't want to get those wrong. So that's back to normal. And when you're copying files, I'll go over that briefly, but you'll want to take something more detailed to or follow a more detailed guide than what I'm about to do. This is just to give you a sense of where these files come from. So to find your disks, do ls_blk. You can see I have two disks, SDA and NVMe 0N1. This is a solid state drive, and this is a spinning platter drive. You can see disk is labeled here, and this is the partition. I only have one partition on this disk. It's called SDA1, and same here. So if I want to copy my disk, I'll use dd, and I'll use the input file. These disks are in /dev, SDA. See, there's SDA and SDA1. I'm going to copy the whole disk, so I'm going to use SDA. And actually, I'm going to just leave it at that. I'm going to pipe this into gzip, and I'm going to compress it with the file name image.dd.gz. I'm not actually going to run this command. I'm not sure how much space this will take up, but I don't want to fill my drive with it. But this is how you make a disk image, and we're going to be using a disk image pretty soon here. So we're back to some layers. Computer scientists love layers. And a disk image is comprised of many different layers. There's the multimedia layer, the block layer, the journal layer, the metadata layer, and finally, what we're more familiar with, the file name layer. So first, let's talk about the multimedia layer. This is all about partition tables. And when you're diving into a hard drive, this is usually your starting point, because you can get the start address of the partition that you want to examine. Next layer is the block layer. This layer is what contains the actual data of all files. And they're split into equal-sized chunks, kind of like a brick wall is composed of equal-sized bricks. And the journal layer, honestly, I don't have a lot of experience with this layer yet, but I know it's used for incremental backup, and it's used to more quickly recover from crashes of the system. Now the metadata layer, this is what we've been kind of alluding to when we talk about metadata. So for Linux, this is all about inodes. And this file system metadata, like we've been talking about, is permissions, ownership, timestamp, blocks, etc. And the file name layer, this is our normal shell experience. We work with file names all the time. And it's sort of the highest layer of a disk image. Now let's talk about the Sleuthkit. You can use the Sleuthkit to traverse all layers. And usually, like I said, you start at the multimedia layer. So here's the different tools for the multimedia layer. These are actual command line tools. And you'll notice that with the Sleuthkit, pretty much every layer has stat, ls, and cat. It's just a different prefix. So for the file name layer, it's f, fstat, fls, fcat. For the block layer, it's blk stat, blk ls. And for the metadata layer, it's I, so istat, ils, and so on. And they all do similar things at different layers. So mmstat will tell you the type of the partition table. and MMLS will print out the partition table. And MMCat will actually print out an entire partition, which I'm not sure when that would be useful, but I'm sure there's a use case for it. And so yeah, the block tools, BLKstat, BLKLS, BLKcat, and BLKcalc. This one's a little different. This is for calculating a regular block number from an unallocated space. That's a little bit more advanced. We're not going to cover that today. The journal has JLS and JCat, and I haven't used those much. Metadata has ISTAT, ILS, ICAT, and IFIND. And ISTAT is going to get you information about a particular inode. ILS is going to list inodes. ICAT is going to print the contents of a file based on its inode. And IFIND is going to find an inode based on its file name or its block number. And finally, file name, FLS, FCAT, FFIND. FLS is going to list all the file names. FCAT is going to print the contents of a file based on its path. And FFIND is going to find the file name based on its inode. So let's get in the weeds with those a little bit. So I have this disk image with this long file name. So the first thing I'm going to do is use the multimedia layer tools. I'm going to print out the partition table. So here's the partition table. The one we're interested in is the Linux partition, and it starts at 2048. And that's going to be really important to remember because pretty much every tool is going to take that offset as an option. So next I might print all the file names on the hard drive. I'm going to use that offset of 2048. Use this image. Okay, so that prints the highest level folders. If I use the -R option, it actually recurses into all the directories. And of course, piping that into less is going to be really helpful. So I can view it all at once in slices. So I'm going to search for a particular directory. So I found conf.d, which is an etc folder. And I'm going to use dmessage as an example. So this number is the inode number for this file. So we can use istat to find out a lot of information about this file. Offset 2048. The image name next. And then this number for the inode number. All right, so here's a bunch of information. As you would expect, it has user ID, group ID, permissions, size, and then it keeps track of how many links to it exists. And here's all the timestamps that it keeps track of. And this is its block number. Before I use that, I'm actually going to cat the file using the inode. Say, use the same offset. It's probably a more efficient way to do that, but okay, so there's the contents of the script. It's a dmessage script. And I can also cat it with the block number. I'm still going to use that same offset and image name, but I'm going to use this block number instead. And yeah, that's the same output. It's the same file. Finally, with fcat, I specify the offset. And actually, with this, the file name goes first before the image name for some reason. So that's etc conf.d dmessage. Right? Yeah, I think that's right. And then it's the image name. So yeah, that's accessing that file 3 different ways using 3 different layers. And I refer to these docs a lot. It's the Sleuthkit commands. It gives a little 1-sentence description of what it does. And it can be really helpful as you're starting out. It's basically a cheat sheet for Sleuthkit. So now that we've used the command line tools, I'm actually going to talk about the graphical method of using these tools. Autopsy is just the graphical user interface, or GUI, to Sleuthkit. And it's a web UI. And it's actually a little bit better for exploration because it's just point and click. It's a little bit easier to explore a disk and get a sense of what's happening and to know what all your options are when you're examining a file system. So let's start Autopsy. Looks like it's already running. Let's see if I can access it. Yeah, it's already running. So all you do to start Autopsy is this and enter, but I have it running already. And this is what it prints out. So you can go to localhost 9999/autopsy to start. And let's start a new case. Let's call it test 18. We can, all this other stuff is optional. Add a host, host 1, that's fine. Let's add an image. Let's add the image file. So it needs the path, so I did print working directory. This is a directory it's in, and then this is the file name. And it's a whole disk, and let's just symlink to it. I'm going to ignore the hash for this example. Let's add it. Okay, it looked like it worked. So here's our file system. Here's the details of the image. Click on File System. And here's just some high-level information, all the metadata information, the blocks, the block groups. If you go to File Analysis, it'll give you sort of a file browser. Just scroll down, find etc conf.d dmessage. So here's dmessage that we saw before using the command line tools, and this is using the graphical method to do the same thing. But it's just a little bit easier to explore using this graphical method. I think most people prefer using Autopsy to directly using the Sleuthkit tools, but it's good to know what's happening behind the scenes with Autopsy in case you run into any snags. And here we can enter a keyword search for Pico. Here's a interesting fragment that we found. And here's a flag. So get one for free this time. So your problem set for today is Sleuthkit intro, disc sleuth, disc sleuth 2, and the Sleuthkit apprentice. Good luck.